Okay, let's start. Good morning. So final stretch. We have 3 classes left this week. And then we're going to have 2 classes next week. And then we're going to have an additional class, but that's going to be for review. So we have in total 5 classes. There's still a lot to cover within the formalism of differential forms. But hopefully by tomorrow, at least we're going to have the fundamental theorem of line integrals. That is to say, a fundamental theorem of calculus for differential 1 forms and 0 forms. So today I'm going to be taking attendance. Okay, so let's remind ourselves the types of things that we were looking into. The standing assumption is always that M is an open subset in some norm space E. Right? I had mentioned how there are 3 perspectives that one can sort of approach differential forms from: the syntactic perspective, differential calculus perspective, and integral calculus perspective. These are stable by themselves. That is to say, if you're just worried about the syntactic parts, syntactic approach, you don't need to sort of figure out what this, that, the other thing means. But if you want to understand it, if you want to have a meaning behind calculations, you need to develop the differential calculus approach. Or maybe, if you only are interested in calculating certain integrals, you don't even need to focus on the meaning. You can just calculate things. But I thought it would be better to have some understanding as to how to calculate things, and then start developing an intuition as to how these things operate and what they really mean. And then on top of that, ultimately sort of connect everything back to integral calculus so that we have sort of like a meaningful Stokes theorem or fundamental theorem of calculus. So just to remind you the types of things that we were discussing and the context and the scope of these different perspectives, the syntactic approach really works for open subsets of Rn. Right? It's spatial. Okay, and what sort of things do we have here? We have these spaces of CK differential P forms on M. Within the syntactic perspective, these are certain spaces of formal expressions. What was K? K was the regularity. K could be 0, meaning I'm looking at coefficient functions that are continuous. Could be C1, C2, C infinity, whatever. Now later on, if you end up taking more advanced classes, what you're going to do is you're going to change, you're going to develop a more robust integration theory as opposed to compared to the Riemann integration. Then you're going to go back to differential calculus, re-understand these regularities. You're going to have different sort of notions of regularity, maybe Sobolev, whatever. And then everything pretty much is going to follow just the same. So the way I'm describing all of these things are very modular. Those of you who are going to need more advanced sort of perspectives will be able to still use the same sort of formalism, except that this is going to be replaced by something else. It's going to be, I don't know, Sobolev or Lorentz, Orlick's, whatever. Or maybe if you don't care about these kind of things, some people, geometers, for instance, they don't really care about different regularities. They just look at C infinity, or even better, C omega, analytic, or even better, polynomial, etc. So this perspective, I think, what I'm trying to say is very modular, even though it may not seem like it for now. In any event, for us, K is 1, 2, 3, whatever, or infinity, and P is 0, 1, 2, whatever. But it's a finite number P. Okay. What else do we have in the syntactic approach? We have this wedge operator. Okay. We have the D operator, exterior derivative. On top of that, we have more things. what do we have? Well, let me first write pullback, phi upward star. And then we have the musical isomorphisms and the Hodge star. Okay. By the way, I'm writing a sort of summary of all of these approaches using my notation. Part of it is because, the formalism is somewhat like complicated. And because of that, typically the presentation of differential forms end up being sort of confusing. So I'm writing a document where I'm sort of listing everything in a regular order, which I hope will be available by the end of the Thanksgiving break. But these are the sort of symbols and objects and so on. Now, we started talking about differential calculus, rather differential forms from the perspective of differential calculus. Here we didn't fix E to be this Rn. We kept E to be this arbitrary normed space, but we still defined CK forms on an open subset. Now I told you that there's again a D operator and a wedge operator, and these two have sort of definitions here. But what we did was, instead of sort of going through the definitions, I just focused on D that goes from 0 forms to 1 forms. Because I told you, from the perspective of differential calculus, exterior derivative of a 0 form is defined as the actual derivative. So let me just say D operator from 0 to 1. Now I'm postponing wedge, general definition of the exterior derivative, as well as these. Today I'm going to define this in a second. So we're going to define later these two. This we're going to define today. And maybe later, even after we define these, we can define these, the musical isomorphisms as well as the Hodge star, because somehow these require more structure than just a normed space. Okay. So these can be defined in this setting. These things use special properties of Rn. Namely that the musical isomorphisms really require that E be an inner product space, and furthermore, as a metric space, that it is complete. That is kind of surprising, but it is true. In other words, for these two, in general, you require E to be a Hilbert space. For this, it's even more special, this Hodge star. For this, you really want E to be an oriented finite dimensional inner product space. If time permits, I'm going to describe what this really means, this orientation. For now, we're not going to use this. And if you think about it, we use these operators just so that we can connect the standard Calc 3 operators to the differential formalism. And so really for integration or whatever, you don't need any of this. And in the fundamental theorem of calculus 2, we're going to need this, and we're going to need something else. And so from the perspective of integral calculus, we're going to say, well, differential forms are things you can integrate. Okay, that's how I had defined it, over certain things. And these things, for now, let's say it that way. These things are, these are called things like chains or cells or currents. These are sort of similar ideas that I'll describe later. So currents, chains, cells. One thing we're going to need is something called the boundary operator. Now, back when we were discussing metric spaces and stuff, we had also talked about something called the boundary of a subset. And if you remember then, what I told you was, well, I don't want to use this partial symbol there because we're going to use this partial in a different context. Much like I reserved this lowercase d symbol so that d squared is 0 after. Somehow, this boundary operator, too, is going to be something that transforms chains. And again, its square is going to be 0. Okay? Boundary operator is going to be something that takes what we're going to call a one cell. This we're going to call a one cell. Such that when you take the boundary of it, it gets rid of this path that connects the two endpoints, but remembers these two. But somehow it also remembers the orientation. In other words, boundary keeps track of the fact that, oh, this was the initial point and this was the end point. So maybe we can say this is plus, this is minus. Okay? So this is not quite the same boundary as boundary of a subset in the sense of topology, in the sense of metric spaces. That's why I didn't want to write boundary of S, a subset. Because note that, and instead of writing it like this, what I wrote was this more bizarre sort of more cumbersome notation, which is boundary. The point there is that in a topological sense, the boundary of the boundary is not 0. Okay? So for instance, if you were to think about the unit ball, unit desk, right? This is not going to be a chain or cell, whatever. But I can still talk about its boundary in the sense of topology. Its boundary is the sphere, is the circle. The boundary of this, if you open up the definition of boundary in the sense of topology, is going to be itself. Okay. So in the sense of topology, this boundary is a different thing. Ultimately then, what's going to end up happening is that we're going to learn, well, we're going to take a P form, let's say. So that its D is a P plus 1 form. Then we're going to integrate d omega over a P plus 1 dimensional space, that is to say, a P plus 1 chain. So once we define this boundary operator, it's going to be so that boundary of a P plus 1 chain is going to be a P chain. And the integral of this on this is going to be the same thing as the integral of this on this. Let me write it here. And this is going to be the fundamental theorem of calculus. It's going to be Stokes, divergence, Gauss, fundamental theorem of line integrals, everything. Everything will be this. Okay? So this is what we're after, ultimately. Any comments or questions? This is just like a preview of what is to come. I'll suggest to you that by the time we get to proving something like this, you're going to say, well, what is there to prove? You defined everything so that that holds. Okay. Okay, so let me define the pullback operator within the context of differential calculus. Oh, wait. Even before that, I wanted to do one more example. Let's first do that. And then I'll define the pullback. So last Friday, we were discussing how to visualize differential one forms on Euclidean spaces, whatever. And one of the exercises at the end of the class I gave you was, well, this idea that, if you know that the differential one form is exact, that is to say, it's the d of something. In this case, it's the d of a zero form. How would you indicate that from a visual perspective? Again, I'm taking M to be R2. First, I want to say one thing. So for instance, let's look at this. Omega equals x dy. I think we had looked at this example. Right. So that's a one form. From the differential calculus perspective, you fix a point. And now this is a linear transformation from R2 to R. In other words, it's a row matrix. And how do you come up with this? Well, the coefficient of dx becomes the first coordinate. The coefficient of dy becomes the second coordinate. In other words, this is just 0x. Okay, I'm thinking of this as a linear transformation from R2 to R. Okay. Now, last week we had discussed how you could imagine this by fixing the position. Right? So we imagine this to be position. And once you fix a position, you have different velocities. And this omega really takes a position information together with a velocity information and gives you back a number. By the way, I looked online on YouTube. What I was calling a speedometer, I think, is what is called a radar gun or a LiDAR gun, depending on what it is, the technology. It's a pretty nice technology, actually. Now, police officers use it, but also like in sports, apparently, people use it quite often to figure out, what is how fast can this player sort of throw the baseball or whatever. And there's, like these instructor manual videos. It says, if I have this guy that's going to throw the ball this way, there's like a pocket radar, whatever. If you want to figure out how fast he's throwing the ball, don't stand perpendicular to him. You're not going to be able to detect the true speed of the ball. It says stand behind him, which makes sense based on our intuition. Okay?
Suppose you can stand in front of him too.
Exactly. Yeah. That's what I thought too. Yeah, that's true. So somehow you want to sort of stay in the same direction in the reality because, okay, I'm, of course, saying speedometer, whatever, in a metaphorical sense. But in reality, there's a certain technology. And what it is that this machine sort of, sends out a signal. It sends out a radar, like sound wave, bounces back, and calculates the things. There's like, police officer sort of manuals and all that stuff too. And on top of that, of course, the beauty of our times, there's also lawyers that have videos about how you can get out of speed tickets. And a big part of the argument is, oh, these devices are faulty and stuff like that. And they list in how many different ways it could be faulty. And so it's kind of funny. But anyway. Last week when we were trying to figure out how to visualize this, I always fixed a point. But ultimately, the differential form itself the differential form itself is not given to you with a specific point position information. In principle, you should be able to set up omega at any point, and it gives you something. And so somehow we would like to be able to assemble all of these pictures, namely these sort of translations of lines, into one picture to represent omega as such, without a specified point. And so how do you do this? Well, what you do is, instead of drawing those lines on the whole plane, you sort of draw them on small windows. That's how I imagine it. Okay. So for instance, here is 2, 0. This is my M. It's my position space. I'm going to draw a small window around the position 2, 0. And in this small window, I'm going to draw what omega 2, 0 is supposed to be. Okay? And so now it is just 2 dy, right? It doesn't see anything in the x coordinates. So it should be something like this. Let's leave it like this. Okay? And what is the direction? It's upwards. Now, when I draw this picture, one of your colleagues at the end of last class asked, oh, these are supposed to be like uniformly separated, right? And that is true, of course. And it actually doesn't matter how sort of, like what the length here is, because this is sort of like a heuristic picture, at least for me. What does matter, though, is when you're trying to visualize the whole differential form using these small boxes, small windows, you want to somehow represent the effect of changing the position. Okay? So you imagine, okay, so what does this picture mean? I should start it from its own origin. It means that if I were to look at this specific velocity, okay, so the y coordinate has length 1. According to the differential form, this has the speed 2. It pierces 2 of the lines, right? Because the y coordinate here is 1. I'm multiplying it with this, but this second coordinate is just 2, so I'm just multiplying it by 2. And I don't care what it does in this coordinate. This specific differential form doesn't see what happens in the x coordinates. Now, when I switch over to the differential form around this point, okay, so now in this window, I'm going to draw omega of 1, 0. It's a different point, different position. But you see, at this point, x is now 1. So somehow, if I could somehow take this small window together with the arrow and transport it this way so that I could use the same arrow that I used here, instead of seeing 2, I should be seeing 1. Meaning, when I'm sort of drawing the red lines to describe this form, instead of drawing it like this, I would be using more sparse lines. More specifically, I would use this expression. This is so that if I could use the same arrow, same velocity I used here, this time I can only pierce one of these lines. Okay? Does this kind of make sense? And so imagine this then. Imagine taking this window and moving it this way. As you keep moving it this way, in a small window, what you should see is, you should see more and more lines. So for instance, at 3, instead of seeing 1, 2 this way, I would be seeing 3 lines like this, for instance. And likewise, if I were to take the window here and look at what happens in this axis, well, in this axis, both of these coordinates are 0. And so there is no speed, right? So the differential form doesn't see any speed whatsoever, which means that all of these lines are going to sort of be infinitely away from the original horizontal line. And then when you keep pushing this way, now it's going to flip. Can you sort of visualize this in your head? Imagine sort of like these lines. You sort of like move this little window around. And at each window, you see a different picture. OK. Take some time. Maybe this sort of visualization doesn't quite work for you. I would highly recommend that you come up with your own method. So now I'm going to look at this example. I'm going to look at an exact one form. OK? So for instance, instead of looking at x dy, I'm going to look at x dx. Okay, in terms of differential calculus, what is this? It's this one. Looks very similar to the one over there, but you're going to see it is very different in a sense. Now, I suggest to you that this is an exact one form. Do you agree with this or no? Some of you do. Well, how do you figure out something is exact? Well, in order for a one form to be exact, it should be of the form df. So I need an f. What's an f? What's a scalar function such that its d is this?
F of xy equals x squared over 2.
Right? It's a function. If I were to take the derivative of it with respect to x, right? 2x divided by 2 is just x multiplied by dx. There's no y dependency, so there's not going to be any dy. Okay, so this is an exact one form. Let's just remind ourselves, in general then, asking whether or not a certain differential form is exact really is asking you to solve a certain partial differential equation. Raoul Bott likes to call these the God-given partial differential equations. And so if I have this, a typical differential one form on Rn, this is exact if there's a zero form such that df equals omega which means that the corresponding functions should be the same, i.e., this system of linear first-order PDEs has a solution F. Okay, because that's what you get when you open up this DF. Now, this does, of course, get very complicated. Differential equations is not easy. They're not. It's not a joke, but we're not going to discuss that too much. But you should at the very least know. And of course, you should also keep in mind that any exact one form is automatically closed. So if I were to ask you if something is exact, a good idea is to always take its d and see if it is 0. Because if a differential form is not closed, it also cannot be exact. Okay. So for instance, I know that that guy is not exact. There is no solution f like that for this guy. Because if I were to take the d of it, I don't get the 0. It's not closed. Let's write this. This is very important. Going back to this example, you have this x dx. How would I imagine this? Well, it's pretty much the same picture as this, except that instead of not seeing motion in the x direction, it doesn't see motion in the y direction. Okay? Meaning, I should be seeing rotated pictures. Again, that's 1, that's 2. I'm going to draw small pictures here. Let me try to draw it better. So that's 2. Just like before, I should be seeing twice the amount of lines that I see here. Because if x is 2, then it's going to pick up more speed, this specific differential form. And just like in that case, if I take this little window and keep moving it this way, I'm going to see within the same small window more and more lines. They're going to be more dense. If I get closer to the origin, I'm going to see less and less lines. If I switch to this direction, maybe we should do that as well. Here's -1. I'm going to see the picture that I saw here, except that it's going to be in this direction. Okay. Another point, of course, is that if I were to, instead of moving in the x direction, if I were to move in the y direction, I'm going to be seeing the same picture, because this form doesn't depend on y. Okay. So maybe if I go here, I'm going to see whatever I saw here duplicated. And so on. Any questions about this so far? Now the question is then how to relate this picture to the fact that omega is exact. Ultimately, I suggest to you that within this picture, I am seeing x squared divided by 2. The point, of course, is that as you keep moving these small windows around, you're actually seeing the level sets of x squared divided by 2. Right? Because x squared divided by 2 how does it look like? It's a parabola. Let me just draw xz. This is how it looks like. And then imagine the y-axis is coming toward you. The graph of this is something like this, right? Meaning, in this picture, when you sort of look at the level sets, you're going to see lines. If you arrange it so that the level sets are uniformly distant, not in the xy plane, but in terms of height, because this is a function that grows quadratically, as you go away from the origin, you're going to see more and more dense lines. These little windows is picking up that. Okay. What it says is, well, I can look at these little windows, and in fact, if I were to look at windows like this, and then like this, and like this. So they keep moving everything around. All of these pictures actually assemble to the level set picture. That's what exactness means. Okay. The same thing doesn't happen here, for instance, because you're going to move this sideways, and somehow you're going to have to just like stop some of the lines. Because as you keep moving it this way, lines are supposed to be sort of separating more. That's how you can see that this one form cannot be exact. On the other hand, that one can. A very nice exercise is to do the same thing with f equals x squared plus y squared. Look at the level sets of this. Now it's a paraboloid, right? Level sets are circles. You're going to see something very similar. Instead of lines, you're going to see circles, concentric circles. Like this. And pictures of df should pick up the tangent lines of these level sets. This is what it means for a differential one form to be exact from a geometric point of view, or differential calculus perspective. And the same perspective holds for E and arbitrary norm space. Matrix space, I don't care. This intuition works in any case. Any comments or questions about this? I feel like you're not happy about something. Well, if it did, I'm telling you, it would be the level sets of the potential function. So D of a zero form, when you visualize it the way I described to you, picks up the tangent lines to the level sets of the form that you started with, of the zero form that you started with. Okay? So that's that. This is the intuition for zero forms, one forms, how D changes a zero form into a one form, what it means for a one form to be exact. We can't quite see what it means for a one form to be closed because I didn't tell you how to take the exterior derivative of a one form yet, but we're going to postpone that for now. Now what I want to do is I want to figure out what it means to integrate a one form. Okay. Now our standing assumption is E is a normed space. Okay. And a form, one form on M, which is a subset in E, is something that we're trying to integrate. But you'll remember, I hope, that we didn't define integration on this more general setting of norm spaces. We required that the subset that we're integrating things on has to be in a finite dimensional inner product space, something like Rn. So the notion of a cell is going to be related to that. Okay. In fact, let me first start with this. I'm going to give a more general definition. Oh, in fact, even before that, I should define pullbacks. I almost forgot. First definition. If M and N are open subsets in normed spaces, and phi is a CL plus 1 function from M to N, then the pullback goes from the space of CK forms on N into the space of forms on M with regularity minimum of K and L. It's a linear transformation defined like so. Well, for any omega p form on N, for any x in M, and for any p vectors on E or in E, the pullback at x is that linear transformation that takes V1 to Vp to this. I had defined this operation using the syntactic formalism. This is how you define it using the differential calculus approach. Let me just draw a picture to describe to you what this is really doing. As usual, we have two open subsets, M and N. And a function phi from the first one into the other one. I have a form defined on N, meaning I have one of these pictures, something like this on N. Well, if I pull it back using phi, now I should have a similar picture on this set. I need to fix a position and a velocity. Somehow I need to transform these into things here. Well, with the position, I can just look at phi of x. With the velocity, I can look at phi prime of x applied to this vector. Maybe it points this way. Okay. Phi transforms the position and the velocity in this way. But once I have a position and a velocity, I can feed it to this one form. That's how we define the pullback for one forms. Like this. Okay. Okay, I think that's a good place to stop. Thank you. We'll continue tomorrow. Okay, let's start. Good morning. So today we're going to finally introduce integration of differential forms. We're going to focus on initially on integration of one forms, get some idea, establish some sort of fundamental theorem of calculus. Probably that's going to be done tomorrow. And then we'll be on our way. So now we're switching over to the integral calculus perspective, even though I didn't write it. A current, or a generalized differential form on M, is a bounded linear transformation that goes from CK differential forms into reals. Bounded meaning continuous, right? So for linear transformations, bounded is equivalent to saying that it is continuous. In other words, I would like to be able to say, if I take a sequence of CK forms that converges to some other form, I want T of omega n, whatever, to converge to the T of omega infinity. Now, we had talked about how to think about spaces of CK functions as a metric space, to say the least, because ultimately, at the very least, if I were to fix one of these indices, one of these degrees, right? So this is like all differential forms, but any differential form is a finite linear combination of differential p forms, where p is, let's say, at least at most 15, whatever. And this is nothing but ultimately a space of CK functions defined on an open subset taking values in some other linear space, some other norm space. And so far we were we were thinking of this space using the so-called CK metric. Meaning, you would say if you were to take a sequence of CK differential P forms, omega bullet, I say that this converges to this guy if for any L at most K, all L derivatives converge uniformly. Uniformly on M. Kind of mentioned though, even though this was not very important for us because this becomes rather technical, and those of you who are going to take more advanced classes are going to worry about these kind of matters more. But I just mentioned this. The one problem here is that this notion of convergence, or in other words, this notion of topology, is rather strict. There aren't that many convergence sequences. Ultimately, because M is in principle unbounded, it's certainly not compact. And so you don't have maximum principal. Derivatives may not be bounded, blah, blah, blah. So I said, technically, this is not a metric, but it's what is called an infinity metric. So it could take the infinity value. And so for application purposes, you switch over to really a much nicer notion of topology on spaces of CK functions. Really what you say is, you want this, but not on all M, but on each compact subset of M. So this is what is called the CK uniform convergence on compacta. And really, when I say continuous, I mean that with respect to that. To CK uniform convergence on compacta. This is just a technical matter. We're not going to really use it. I'm not going to ask you to take sequences of, differential forms, take subsequences of them, whatever, so that you get something convergent. But that's how we use these kind of things in principle. Everything that we discussed earlier in the class applies to differential forms. And in fact, many of the currents that we're going to discuss is going to be a lot more convergent. In other words, the types of currents that we're going to look at in this class are going to have more convergent sequences. I'm going to call a current a P current if for any form that is not a P form, it is 0. Is a current T such that for any Q not equal to P, and for any Q form, for any omega CK Q form, T of omega is 0. So it only does non-trivial things to P forms. In that case, I'm going to call it a P current. The world of currents is rather complicated. That's why I'm not even introducing a notation for the space of currents. Because ultimately it turns out that any differential form itself is a current. interpreted properly, and that's why some people also call this call currents generalized differential forms. We're just going to look at very special ones. L plus 1 p cell in M, okay, is a very specific type of p current that I'm going to define in a second, at least for p equals 1. Well, let me say, this is not the definition, is a special kind of p current, and a Cl plus 1 p chain is going to be a linear combination, finite linear combination of Cl plus 1 p cells as a current. In M is a linear combination of Cl plus 1 p cells. One thing too, I'm going to introduce other notation as well, but typically in situations like this, instead of writing T of omega as the output, you write it like so. I'm going to use the, so to speak, physicist's notation here. I'm going to use the bra-ket notation. Sort of combining T and omega together, and that gives me the output. Okay, that's the type of notation I'm going to use in a second. So let's just focus on p equals 1, because ultimately, like I said, I want to at least discuss integral calculus for differential bond forms. A Cl plus 1 cell, there's a definition of 0 cell as well, but we're going to get there later. On M, okay, ultimately, this should be something that you can feed a 1 form into that produces a real number in a linear fashion. Whenever you see something like this, whenever you see, oh, I have something that takes functions, turns them into numbers, and does so in a linear fashion and continuously, you should say that should be some sort of integral. Okay. Is defined as, let's say, capital C gamma semicolon alpha to beta. These are in brackets. Okay. Now, what I'm going to do is I'm going to tell you what these are, and I'm going to tell you what this is as a linear transformation on differential bond forms. Where alpha and beta are real numbers. I, even though I didn't write it here, is some open subset, is some open interval that contains alpha and beta. Well, let's write it like this. Okay, that's fine. Alpha is an open interval containing alpha and beta, and gamma is a Cl plus 1 function from I to M. So it's a path. Okay. So that's what that notation means. And now I need to tell you what that t is as a linear transformation of differential on differential one forms. Let me write it here. For any ck one form, okay, so I'm saying, oh, this is a linear transformation on differential one forms. I'm feeding to it a differential one form. I want whatever this is to be a number. Well, you're going to pull back omega using this parametrization. Now you have a differential one form on the interval. And then you're going to integrate that over from alpha to beta in the directed sense, in the sign sense. And what does this mean? It means okay. Now this final integral is the sense of signed integration in one dimensions that you learned in 3210. Okay. So let's first think about how this makes sense. I just look at this expression, okay? Gamma goes from I into m. If I were to fix a time, its derivative then, let's parse this. For any t in I, gamma prime of t is a linear transformation from the vector space of the input to the vector space of the output. But any linear transformation from R into some vector space is, you can identify it as a member in that output vector space. So gamma prime of t is a vector in E. This is a position. If I were to fix a position inside omega, now this is a linear transformation from E to R. So you have a path, okay? At each time, you look at its velocity. You take that velocity, feed it into the differential form at the appropriate position. Ultimately then, even though this looks very bizarre, what you're integrating depends only on t. It's a single variable function. That gives you a real number. So what you're integrating here is an object that you learned how to deal with in 3210. Okay? And so that's what I mean when I say just integrate it like you learned in signed Riemann integration. And what do I mean by signed? This is from alpha to beta. Okay, alpha to beta, but I didn't say that alpha is to the left of beta. Maybe alpha is 15 and beta is minus 5. Okay, so 15 to minus 5, you would flip this if you want to integrate it, but you would pick up a minus. Okay, that's what I mean when I say signed. Okay, that's the definition. It's a mouthful. Somehow, the way I think about it is like this. So this is, once you spend some time, sort of like a natural way of coming up with a linear transformation from differential forms, or differential one forms to say the least, into reals, what is this doing, right? So you have here your interval, and you have some open subset, M, inside E. And on M, you have this differential one form, which we learned how to visualize earlier, yesterday and last week. It's like you have like this little window, and you look around, and you see sort of a bunch of lines. Okay? And so you fix, let's say this is the positive infinity direction. You fix 2 points, 2 endpoints. Let's say alpha is larger than beta, just to reiterate. But you're going to integrate from alpha to beta, right? Because even though in the interval, it kind of makes sense which one is larger than the other one, in this multivariable setting, you cannot just say, oh, this guy is to the left or to the right. So you have to choose. You have to say it explicitly. Let's say something like this. This is gamma of alpha. This is gamma of beta. Goes like that. And so now I'm imagining my differential one form to be something like a skateboarder, okay? And now this is like a rail that you can sort of slide on. At each point, you see, sort of like your skateboarder takes his radar and somehow keeps track of the path he's chasing. At each time t, you're at a different position. You have like different sort of entries in the matrix that corresponds to this one form. You look at the velocity, it tells you something. And then you add all of these measurements up. And that's what this current does. OK. Any comments or questions about this? Now, I'm not going to test you on currents in general. The reason why I described it this way is because ultimately what matters ends up being to be this pairing. Okay? On the one hand, you have things that you can integrate, right? Differential forms. And you have things that are integrals ultimately. In a sense, it doesn't really matter which one you think as integral. Somehow you have one thing in sort of like the other type of thing, and you can put them together, and ultimately it gives you a number. In other sort of textbooks, so for instance, those of you who are going to take topology classes, you focus on this space, the space of cells, whatever, and then define differential forms to be integrals on cells. You define it the other way around. Because we sort of spend a lot of time on differential forms, I'm defining everything else in terms of differential forms somehow. OK. I think what's going to be useful is if we did some examples. I should also mention the more classical notation for things like this, of course, is you would say integral of omega over gamma. So let's write it here. So you would see what I write as this. So this would be what people call a line integral. Or you could also see this, where gamma is the image. So in Calc 3, probably you saw one of these notations. The point is that you're not integrating over a subset. Okay? It's more complicated than that. It has this directionality associated to it. So for instance, if you remember your Calc 3 calculations, you have sort of like a region here. And then you have its boundary. But they say oriented in such a way that the region over which you're integrating is always to the left or whatever. Okay, it's not merely just a subset over which you're integrating. It's something more complicated. OK. So let's do an example. Omega is on R2, and it is y dx, x dy. Right, this is a C infinity 1 form. On M, let's define gamma to be the path that takes t to 1 plus t, 2t, 1 plus 3t. OK. I still don't have the current, you see. I need to tell you something about the endpoints. I need to give you alpha and beta. And I need to tell you in which direction I should compute this. So let's say alpha is 0, beta is 1. In fact, let's do this. I'm going to keep m and omega. I'm going to change the paths and the endpoints a little bit. So this is the first example. Okay. Now I want to compute this integral. So what do I do? First, I need to figure out what this is. OK. And so how do I think about this? Gamma of t gives me my position. And at any position xy, I know that omega should be the matrix with entries yx. Right? So this is going to be a row matrix, 1 by 2. The first entry is going to be y. But y in this case is this. OK? So does this make sense? Right? Because this is x, this is y. It depends on t, but no, that's fine. Now this is a linear transformation from R2 to R. Okay? It's a row matrix. Now I need to feed to it the vector that is gamma prime. Let's compute that. Oh, I should ask you, what is this? At any time t. 3, 2? It's 2, 3.
Oh.
Yeah?
Oh, yeah.
But with the velocity, you're not switching. The switching comes from the form itself. That's, yeah, it is confusing, but that's how it goes. Now you take this, feed it to this. OK? So you just take the matrix multiplication. What is this? So this is a dot product. What does it give you? It gives you 2 plus 5t plus 3 plus, 2 plus 6, 2 plus 60 plus 3 plus 60. which ultimately is 5 plus 12t. Okay. So this thing, you see, which again, let me reiterate, is the one form. And really, OK, I'll mention that in a second. But ultimately, this is the thing that I'm integrating. This is the guy I'm integrating. Okay. Now I put it in the formula. I need to integrate this from 0 to 1. And so right. Let's write alpha and beta as well. Alpha is 0 here, beta is 1. This is the thing I'm integrating. I mean, I'm sure at this point you can do it, but let's finish it up perhaps. 5t plus 6t squared. T goes from 0 to 1. Right? This is the plus, this is the minus. Okay, minus doesn't exist because there's a factor of t. The other side gives you 11. Okay. So this specific one cell associates to this specific one form the number 11. Okay. Now what would happen if I were to say alpha is 1, beta is 0? Okay, that's the other example. Let's look at that. Well, now, what is this? Well, the integrand is the same. But you're integrating from alpha to beta. You're integrating from 1 to 0. Okay. So what is this? Okay, very good. Any questions so far?
The math wasn't too bad, but like, what was this example like? Was this just a line integral?
Yes. Yes. But of course, what I'm trying to say is that the same formalism works for differential one forms defined on matrix spaces, whatever, if you want. It's literally the same formalism. That's what I'm saying. Okay? Yes?
Why is 1 plus 3t above 1 plus 2?
Uh-huh.
Can you move the plus x dy on the other side?
OK, that's a good point. The reason why, OK, so what your colleague is suggesting is when I'm figuring out the linear transformation or the row matrix associated to this point by omega, why did I take this and put it here as opposed to here? And I think your colleague is suggesting, oh, is it because I wrote this later? That's not the reason. It's because x is next to dy. The coefficient of dy gets into the second spot. Very good. this is a very important idea. Whatever you see next to dx gets into the first spot, okay? And whatever you see next to dy, different color, you plug in to the second spot. Okay. Okay, let's do this then. So let's switch the entries. So omega now is x dx plus y dy. Okay. Gamma same. Let's say alpha is 0, beta is 1. Okay. Now, what you suggested should be the case. Okay. And so, what is this? Okay, like so. Gamma didn't change, so this one is going to be 2, 3. Now this, you see, in the first entry, I'm going to see whatever is next to dx. Dx at gamma of t is this. Okay. But I switched the form, you see. It's important. Switch the form. That's a different form. And so what is this? 2 plus 4t plus 2 plus, hang on, 3 plus 9t, which is 5 plus 13t. Now I'm not going to finish the integral, but this time you're going to integrate this guy. Okay, maybe just a, okay, I'm going to leave it as is. Any other questions? Okay. One more example. Now I'm going to change the parameterization with the same path, but I'm going to, instead of use t, I'm going to use 1 minus t inside. Okay. Oh, okay, let's leave this. That's the definition. Go back to the original one form. In fact, let's write it like this. Phi is going to take s to 1 minus s. Okay, this is an affine diffeomorphism of the reals. Let's say alpha is 0, beta is 1. Okay, gamma the same. Now, instead of integrating omega against gamma, I'm going to apply this change of coordinates first. Meaning, let's say beta to alpha. That's my cell, my current, and I'm feeding to it omega. I want to compute this. Okay. Well, you see now I need to look at this path. So what is this? This is 1 plus 2 times 1 minus s. 1 plus 3 times 1 minus s. Collecting terms, we have 3 minus 2s, 4 minus 3s. That's my new path, okay? That's a different one cell. What is the velocity vector? Minus 2 minus 3. What is omega at a typical time s? In fact, let's multiply this as well. Now I need the coordinates for omega. Omega was x dy, y dx. In this entry, I should be seeing y, but y in this case is this. And then x in this case is that. Okay? Now you do this multiplication. I'm not going to finish this. Okay? You compute something. Okay, I'll leave it to you. It's very important, at least in the plane, in 3 dimensions, whatever, to experiment a little bit how this whole thing operates. That is very important. So let's think about some rules then. I think I'm going to leave this to you. First of all, if I start with a cell like this, and if I were to switch the orders of alpha and beta, I'm going to get a different cell, and it's going to be exactly the negative of the original cell. Cell, again, remember, is a specific thing, specific current, that linearly transforms one forms into numbers. So I'll write it there. There's one more thing I want to say about this. Maybe this equality, but I'll mention it later. This is kind of bizarre, but whenever you see this symbol, you should say, oh, this is a linear transformation that transforms one forms into numbers. So what I'm going to write is, this is equal to minus this guy. Okay. What does this, oh, alpha to beta now. What does this mean? If you were to integrate a one form along gamma from alpha to beta, it has to be minus the integral of the same thing, but from beta to alpha. Based on the rules of Riemann integration, I should pick up a minus here. That's what this means, in short. Perhaps a more surprising thing is, and this is something that you're going to realize or recognize somehow, ultimately when you do this exercise. The change of variables formula that you learned in 3210 allows you to say this. For any diffio phi, this linear transformation on one forms is the same thing as this linear transformation. Okay. Take two numbers, 2 points, alpha and beta. But if you're using as your path this specific precomposition path, you get to change variables, but the endpoints of the integral should be adjusted accordingly. Now, when I write this notation, this means that if phi prime is negative, in other words, if phi is a decreasing function, then what could happen, in principle, is that if this is positive infinity, let's say, this is alpha to beta. Well, I guess I should do it this way. Phi of beta, phi of alpha. What could happen is, when you do this change of variables, your original integral that goes from alpha to beta maybe needs to change the direction. But whatever this phi does is going to adjust the sign of the integral that you should be computing automatically. Okay? I like this notation because of that. Algebraically, you can sort of keep track of, should I be putting a plus, minus, whatever. Okay. So this is all there is to it when it comes to integration along cells. What is a chain? What is a one chain? Well, it's a bunch of these. So for instance, example continued. We can do something like this. Okay. Same omega, gamma, and alpha and beta. As here, let's say. This is a cell, okay? I'm scalar multiplying it by 2 over 11. What does that mean? This is a vector in the space of currents, I'm imagining, and I'm scaling this vector by 2 over 11. But I still need to tell you what this is as a linear transformation on omega. Well, it's going to be nothing but this against this multiplied by 2 over 11. In which case, what we're going to get is 2, okay? Now, in the textbook, when you see I'm taking these and I'm taking formal linear combinations of such things and blah, 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 this is sort of like one way of not thinking of these formal linear combinations. Because either you sort of think about currents as, cells or chains, whatever, as currents, linear transformations on differential forms, or you say, well, I get to take linear combinations abstractly, and somehow I can make sense of these. In the textbook, they say, oh, I'm just going to take abstract linear combinations like this, and I'm allowing myself to do it somehow. Or, if you're like me, this is somewhat more relatable as far as I'm concerned. It's a linear transformation, okay? I can add matrices. That means I should be able to add currents. That's how I imagine. Okay? And now the fundamental theorem of line integrals is very close. It says something about what happens to exact one forms. The remaining perhaps 2 minutes, I can just give you a preview. We're going to finally start doing proofs again, but I feel like you're going to feel cheated because I'm just going to be applying the definition ultimately. Somehow this formalism of differential forms is such a high-level thing, and it works so beautifully that like everything proves itself basically. And so, for instance, I look at this one cell on df, an exact one form. Okay, I open this up. But for zero forms, df is the same thing as f prime. Oh, but this is a chain rule. But then, using the fundamental theorem of calculus in 3210, this is nothing but this thing evaluated at the endpoints. So this is the proof of the fundamental theorem of line integrals. I proved it by mistake. But we're going to write it more rigorously next time, and we're going to be on our way. Okay? Thank you. I'll see you tomorrow. Okay, let's start. Good morning. So, well, we have 3 classes left. 1 today, 2 classes next week after the Turkey Day or Thanksgiving break. And then we're going to have a review. So that's all there is to it. This is essentially the plan. I'm going to mention this in a second. I wanted to mention a couple more things, logistical. One of your colleagues at the end of last class asked about this problem set grading matter. So earlier this week, I sent an email saying that your lowest 5 grades from the problem sets are going to be dropped for the purposes of the final letter calculation. So that's individual. It's not based on the average. For each student, you look at, Canvas looks automatically at the lowest scores and drops 5 of them. And so some of you see 100% from the problem set section on Canvas right now. That means that you cannot get any better, okay? So you cannot get any more grades from problem sets, which means that you don't have to turn in the problem set that is due this Friday and the one that is due next week, but the contents of it you are responsible for, okay? You still, even if you don't have 100%, you still don't have to return it, of course. But
Also, you're still not guaranteed 100% because you could have.
Yeah. That's the point. Yeah. If you're already at 100%, like that means that it doesn't matter whatever you do. You can decide to turn in, not turn in, whatever. You're going to get 100%. You're right.
That's not quite what I'm saying. I'm saying.
Oh, what are you saying? Sorry.
Well, if you haven't, because those will count as 0, and so if you have like 6 10s and a 5, you'll have 100% right now, but not necessarily if you have another 0, is what I'm saying. So like you're not guaranteed.
Really?
Well, like if you got 100% all of them, then yes.
Well, okay. So let's count it the other way around. There's going to be 12 problem sets in total. If I'm dropping 5, that means 7 of them are counted.
Yes.
So if you have 700%, 10 points, that means you're going to get 100% here. Good. Okay. To clarify, that guy knows his math. Okay, good. Is this clear? So what's the point? Of course, the point is that ultimately, the grade itself is not really that important of a matter for me. As far as I'm concerned, from, based on my teaching philosophy, assignments, grades, these are just tools that I can use to get more out of you, make you work better, more perhaps. So now, for instance, a lot of you have very high grades, but now there's the final. It can still, things still can go south. And so now you're defending your title, okay? That means that you're going to have to work a little bit more, perhaps. These are psychological tricks. Anyway, so that's that. And ultimately, throughout this semester, I was impressed by your performance in general. You sort of showed up, It got more and more complicated, more and more abstract, and, We went through a lot of different things. Lots of things happened, but you showed up, and that's what matters. What matters is you spending the time. Right? So initially, when we start learning math, they tell you, what matters is the solution. That's, like solve for x, whatever. Then you go to college, and they start asking for justification. Then you start taking, more advanced classes. In 30-10, justification means a specific thing, they say. It's a proof. Sometimes you say, oh, it is justified. But they say, no, it's not. Not enough. But now that we're sort of, going even more advanced, I think it's safe to say, coming up even with the justification often is not the point. The point is spending the time, getting confused, and being comfortable with being confused. OK. So here is what is left, what's on the menu. A bunch of things I'm going to drop. Probably I'm not going to discuss. So in differential calculus, we still have the wedge operator and the d operator to define. There's a bunch of like Hodge star type stuff. I didn't even mention this d star. It kind of shows up in divergence. This is star d star. And then once you have d star, you define a Laplacian. Once you have a Laplacian, you define a Dirac operator, which means that you have the wave equation, heat equation, all that stuff. So you have like a big part of physics here. Probably I'm not going to spend any time on these, but I'm writing a set of notes. I'm going to be probably mentioning, or at least defining them. I had mentioned, there's a way to visualize high order forms as well, but probably I'm not going to spend time on this as well. I'm going to let that go. Because I'd rather prove some stuff. For the past few weeks, I was just defining things. Starts to feel, not like math. I'd rather focus on things that we can prove. So probably I'm gonna let this go. In integral calculus, we have a bunch of things remaining. 0 cells, 0 chains. There's plus and minus. These are orientations. P cells, P chains. This boundary operator. Boundary operator from 1 cells to, or 1 chains to 0 chains, and something called the push forward. Again, this I probably am going to let go. It's pretty much sort of the opposite of, or the transpose of pullback. I'm going to put it in the notes, but I mean, it is in the notes right now, but probably I'm not going to spend a lot of time discussing it. Then, of course, what is the most important thing, the main reason why we're discussing differential forms, fundamental theorems of calculus. Now, in 30-10, we discovered, we talked about 2 different types of fundamental theorems of calculus. One of them is the integral of the derivative, and the other one is the derivative of the integral. Right? And so FTC1 says, well, if you have something like this, let's say from alpha to beta, then this is f of b minus f of beta minus f of alpha. This is the integral of the derivative version of the fundamental theorem. And then the second fundamental theorem of calculus says the other way around. Now you start with a function, right? You integrate it with one of the endpoints arbitrary. Then you say, oh, this is a function of x. Let me differentiate it with respect to x. And you get back the thing inside. Do you guys remember these? And so when we were talking about, Stokes theorem and stuff like that, that's really the analogous statements in multivariable calculus corresponding to the first fundamental theorem. There is also a statement analogous to the second fundamental theorem, and that is what is called the Poincare lemma. Now, if I were to ask you which one of these is perhaps more natural? Which one would you say? 1 or 2?
2.
Really? Maybe that's like a matter of like personal taste, but I find 1 more reasonable, more natural. Because ultimately, to me, this looks like a very bizarre of a thing. It's an integral, but one of the endpoints is the variable. It's the independent variable, whatever. Now imagine how you actually define this. You fix an x, you set up the lower upper root sums using that x, so you have partitions that ultimately depend on x as well. You sort of take limits, blah, blah, blah. Ultimately, it comes up as a function, and miraculously, of course, f has to be differentiable, whatever. If f is nice, this too becomes a nice function. To me, that's rather bizarre. Of course, from a differential equations point of view, you're actually solving this equation for g. You're saying any solution to this equation is of this form, whatever this means. To me, somehow, this looks a lot more natural, a lot more intuitive. But ultimately, it's a matter of taste, of course, and for some people, it's the other way around. But in any event, from the perspective of this idea that this fundamental theorem of calculus 2 is really about solving a first-order ordinary differential equation, I would say that 2 is more complicated, at least from my perspective. And so likewise, somehow Stokes, once we stated, even though I'm not going to prove it in general, I'm just going to state it, I will assure you that it's going to follow essentially by definition. Whereas Poincare, the analog of this second fundamental theorem of calculus, is going to look rather bizarre. It's very, it's a very natural idea again. It's not crazy. It's very natural still, just like anything else Poincare did. But most of them. It's going to take some time. But, one thing we can say, even at this point, is somehow this formalism of differential forms allow you to just write very nice equations. So for instance, Stokes, that is to say fundamental theorem of calculus in multivariable calculus, is just this. So somehow this, pretend that these are sort of like something like dot product. So this boundary ultimately is something that is like the transpose of this D operator. Okay. That's what we're going to see. For fundamental theorem of calculus 2, rather the Poincare lemma, we're going to have something called the homotopy operator, capital H, that satisfies this. Somehow this H is something like doing this integral in multivariable calculus we're going to see. Okay? So this is what we are going toward. And so the order in which we're going to do these things is enumerated. And in fact, we're going to do this today. We're going to define 0 cells and 0 chains. Okay? I'm going to give you the definition of the boundary operator that goes from 1 chains to 0 chains. Then we're going to state and prove Stokes for 1 cells. Okay? These I hope to be able to do today. And then we're going to continue. Once we're done with the sort of 1 chains and all that stuff, we're going to go back, define wedge and exterior derivative from the perspective of differential calculus, then define orientations, then define p cells and p chains, then define the boundary operator in general, then state Stokes in general, which is going to be this, but we need to make sense of every single symbol involved there. Then we're going to state Poincare lemma, second fundamental theorem for arbitrary p-forms. And then finally, we're going to prove Poincare lemma for one-forms. And then we're going to wrap up. OK? So that's what we're going to do. Now, in terms of what you're going to be responsible for, or what I'm going to take you to be responsible for, there's going to be sort of like a some notes, let's say, a summary of all of these different symbols and how they operate and everything that I'm writing right now. I'm already at like 35 pages. So it's rather involved. And all of these symbols, takes a while to, internalize and digest and stuff like that. But I hope at this point you're starting to see how these symbols somehow are so high level and they have their sort of internal logic such that a lot of calculations in calculus become rather sort of automatic. So I'm not going to take you to be responsible for things in that document. Okay? What you're going to be responsible for are going to be the things that we discussed in class. Certainly one-forms, one-chains. When it comes to line integrals, how to visualize differential forms, all that stuff, differential one-forms, you're going to be responsible for all of these, as well as the contents of the problem sets, but not sort of more advanced stuff that I'm not even going to mention, like the Laplacian and all that stuff that is going to be in the notes. Okay? So that's the agenda. Any questions or comments? Okay. When I was designing this class, I wasn't planning to do as many examples in class, but throughout the semester I did, and ultimately we sort of ended up needing to cut down on some of the topics, which I think ultimately ended up being a good thing. But anyway. So, what do we need to do? Okay, we start with this. 0 cells and 0 chains. Okay. Now, let's remember, chains are always going to be linear combinations of cells for any p. And any chain is really a current. That is to say, when I say chain and cell, blah, 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 even though I might draw pictures, I really mean, oh, these are linear functions that transform differential forms into numbers. Okay? So, a 0 cell in M, M as usual is an open subset in some normed space E, is a current. It's a 0 current. So it transforms 0 forms, scalar functions. And I'm going to write it like this. Lowercase x in brackets. Where, well, this is rather simple, x is any point in M. I need to tell you what this is as a linear transformation on 0 forms. Defined by, for any f, zero form. Remember, I want to use that notation, the bra-ket notation. So I need to tell you what this number should be. Well, it's going to be nothing but f of x. You take your 0 form, evaluate it at this point. We used this, in fact, all the way back in week 1 when we identified the real line, so R with the linear transformations from R to R. We used exactly the same thing. Did you guys see something like this before in sort of like a perhaps more applied context? In more applied contexts, this bracket x is what is called the delta function at x. And typically, you'll see in engineering and stuff this notation. Because for a lot of people, linear functions that transform functions to numbers are integrals. And so even in this case, they would write it like so. Like this doesn't really make much sense. And in fact, you would see, for instance, if you were to take differential equations, whatever applied math, they would say, oh, this delta function actually is not a function. Okay, they say, oh, it's a generalized function. It's something. So this is what is called the Dirac delta or delta at x. So this is what is called a generalized function or distribution. Dirac was one of the famous physicists of his time, and this square root of the Laplacian is also one of his, that is also attributed to the same person. So you should say to yourself, whenever you see something named after Dirac, that's an important thing, even though it looks bizarre. And in fact, a big reason why people established the theory of currents is to really understand things like this that people in engineering and physics were using. They would say, oh, I have this delta function, but it's not really a function. So what is it from a mathematical point of view? And then they realize, oh, here's a current, whatever. We're going to come up with a different thing. It's a function not on M, but on a larger space, on a different space, which is a space of forms. In any event, that's a zero cell, okay? What is a zero chain? It's a linear combination of these, finite linear combination of deltas. And so I would have something like the C equals, let's say, I from 1 to n. Well, AI, these are constants, numbers, times xi in brackets. So you have here the point masses. And what is this? This is nothing but this guy. That's a zero chain. Okay. Why do I need this? Because here I want to think of this as a line integral. In other words, I want to think of this guy as a one form, right? It's, in fact, in one dimension is exactly df. Okay. And I'm integrating it over a one cell. Well, ultimately, I want to say here, this should be the integral over a zero chain. Okay? So I want to write it like so. So in our notation, df on this side, and then this interval from alpha to beta, like this, is, well, bracket beta minus bracket alpha applied to f. in terms of currents, I would like to imagine this. Okay. So somehow, this is going to be my one cell or one chain. And this is going to be my zero chain. That's going to be the boundary. And so I'm going to define the boundary from 1 cells to 0 cells so that that holds. Okay. The boundary operator on, let's say, CL plus 1 chains so I'm going to use the partial symbol. This is a space of all CL plus 1 chains on M. This doesn't really matter for 0 chains, but it's fine. Is a linear transformation defined by, well, all I need to do is I need to describe what it does to 1 cells, because any one chain is a linear combination of them. So what was our notation? A parameterization, and then alpha to beta. Okay. This is Dirac at the endpoint minus Dirac at the starting point. That's how we define it. So this plus and minus is important, okay? Remember yesterday I mentioned how alpha could be a number larger than beta, in which case the direction matters. So these are signed integrals. This is an integration. It's a current. When I take the boundary of it, I should get these 2 Diracs in this specific orientation, we're going to say. Just to give you an idea, just erase this. So here's how I imagine this boundary operator. So this is, let's say, M. I have a one form, let's say, because ultimately I'm going to integrate that one form over this. Let's not draw that one form. Rather, I want to think of a one chain. So it's a bunch of like paths that are oriented. They don't need to be connected to each other, okay? Technically, these could intersect itself. Maybe there's like a bunch of intersections. Maybe there's like a solenoid type of thing. Okay. These are all valid. What matters is that there's always directions. Okay. But maybe some of them are like this. Maybe you join some. Okay, like this. So this is the picture of a one chain. That's how I imagine this. When I apply the boundary to it, okay, now I'm going to have a zero chain. A zero chain is a bunch of point masses or point charges. Okay? But you get to multiply by any scalar function. The one chain, the zero chain that is the boundary of a one cell is a certain linear combination it's so that this is oriented with a plus. So you evaluate the function, the zero form, on this, but you multiply it with a plus, and this comes with a minus. Okay. This is with a minus. This is with a plus. This is with a minus. This is with a plus coming from this part, but it also has a minus, so it cancels out really. It doesn't see it. It's almost like electrical currents. It's almost like that's why you call these currents. These two cancel out, and you have a final plus. Okay. That's sort of the visualization. And what is then the fundamental theorem of calculus, FTC1, for one cells or one chains? It doesn't really matter that much. We can say this. Okay. Let C something like this be a CL plus one cell in M. Okay, so I'm going to take the boundary of that, which means that ultimately I have this, but I need an F. But I need an F that I can take the D off, which means that I need to take a K plus 1, 0, differential 0 form. Then, what do we have? The 0 form, that is F, integrated on the boundary of C is dF integrated on F. That's the statement. Yes?
Can I ask clarifying questions about the picture?
Yeah.
So the one chain is the linear combination of all those curves. Does that mean like each curve by itself is what a one cell is? Like each of those sort of
Yes.
paths by itself?
Yes.
Okay.
I mean, okay, so technically, when I write this, that's a good point. Ultimately, you can't think of it that way. From an applied point of view, you would think of it that way. But formally, you would say, oh, this is a subset such that there is some open interval, which is a closed subinterval, and there is a sufficiently differentiable function that goes from here to there. Okay. So ultimately, even though maybe I have sort of intersections or maybe lots of sort of rotations and stuff like that, when you look at this, there's like a beautiful 3210 type Riemann integral underneath. Okay, so the picture could be misleading, is what I'm trying to say. Does this kind of make sense a little bit?
Kind of. I'm just trying to like kind of visualize the difference between like 0 cells and chains and 1 cells and chains. I'm getting a little lost in like what they.
I think of it like this. 0 cells are supposed to be 0-dimensional integrals. Okay, these are integrals over 0-dimensional things, dimensional. 1 cells should be line integrals, ultimately. Okay.
So what does an integral over a 0-dimensional thing look like?
You just evaluate the function. Over a 0-dimensional thing, the only thing you can integrate, as far as we're concerned, is a 0 form. A 0 form is the scalar function. You just plug in the value.
I'll think about it.
Yeah. Yeah. Yeah.
Is a 2-cell like a surface integral?
Yes, we'll get there. Yes. Yeah, we're going to define a 2-cell, 3-cell, whatever, so that instead of an interval, instead of sort of integrating as we learned in 3210, you integrate as we learned in 2 weeks ago, 2 or 3 weeks ago in this class. It's going to be unsigned multivariable integral. Yeah. I mean, these kind of things are important, but you have like coil type constructions in engineering things. So it's like if I were to think of 0 to 10 pi, well, let's say from R to R2, t goes to cosine t, sine t, function that many of you used in the previous problem that I just graded. Right, so it just sort of gave you a counterexample for this averaging problem. Well, this one cell looks like this. But if I were to use, so this is not quite a one cell is what I'm trying to say. It's a path, it's a function, all that stuff. But if I want to get a cell, I need to specify the endpoints. The endpoints of my integral could be from -2 pi to 6 pi. Okay. So now, even though you see one thing, one loop, you have to integrate over it multiple times. Okay. Just take this example, go through the formalism that we discussed yesterday, compare it to the integral of the same thing from 0 to 2 pi, for instance. You're going to see 8 times whatever. You take sort of one form on it, whatever. I'll leave that to you. The way I'm describing all this is, so the formalism is very robust, even though it looks bizarre. It will be very expressive once you get the hang of it. Any other questions? So in classical form, instead of writing it like this, you would write it like this, of course. You would write it like that, or maybe like this. C. You would write it like this. Now, probably you're used to this notation for surface integrals or whatever, but we're defining everything so that it works. It's going to work for any chain whatsoever. Okay. If you start with a one-dimensional thing, its boundary is going to be a bunch of zero-dimensional things. Of course, in principle, your cell could be a loop and stuff like that, in which case your boundary would be 0, in which case the integral would be 0. But let's not get there for now. OK. Any other questions? How do you prove it? Well, you just open up the definition. I'll prove it here. I'll prove it here. OK, I want this to be on the board. I, in fact, proved this before stating it yesterday. Just follow the formalism. It produces the proof for you. But let's be a little bit more clear. Let's do it slowly and verify that everything makes sense. Let's start from the right-hand side. Okay. Now, instead of C, I substitute this more expressive expression for it. Okay. Now, what is the benefit? What is the difference between the C notation and this notation? This is useful when you're trying to calculate things, but it is misleading because it feels like if you're using this notation that whatever this current is actually depends on gamma. It depends somehow, but it's not very dependent. In other words, if you were to change coordinates here, switch over to something else, use a different parameterization, insofar as you get the right current, insofar as you get the right linear transformation on forms, it's going to actually be the same thing. So the innards, if you were to change the parameters of gamma, the innards of this one cell is going to change, but ultimately, as a linear transformation on forms, it's not going to change. It's going to be the same thing. So that's why it's often good to think of sort of a cell as a linear transformation. It's a current, whatever. It's something inside M. It doesn't depend on some external thing. OK. We define this by declaring what this means, right? So this is supposed to be a linear transformation on this. And I need to open this up. It's a Riemann integral from alpha to beta of what? That's my one form, right? That's my one form. I need to station it at the position defined by gamma of t. Now it's a linear transformation on vectors. I need to feed to it the corresponding velocity vector. Now this is a number. Okay? This is my integrand. Okay? This is, it only depends on t. It's a single variable, real valued function. Okay? I'm going to integrate this, however I can do after 3210. The point here is that we defined the exterior derivative of a zero form to be f prime. Okay? Remember, I postponed the derivative, the exterior derivative for higher order forms. We're just looking at one forms, or zero forms rather. Then I see, oh, this is the derivative of f composed with gamma after chain rule. Okay. Now at this point, I can use FTC1 from 3210. Okay. This was something that we proved a long time ago. Okay. And it says this is nothing but this minus this. But then you say, oh, this is nothing but f evaluated at gamma of beta minus f evaluated at gamma of alpha. But then this is nothing but the boundary of this one cell acting on the zero form, f. Write it here. Well, I'll write it over here, actually. Much easier. And so this is this minus this acting on f, which is defined to be the boundary of this guy acting on f. So if I start with a d exterior derivative on the form side, I can transfer it over to the chain side if I use this boundary symbol. At a high level, this is pretty much integration by parts, actually. That's actually how I think about it. It's integration by parts. Does this kind of make sense? It's like I say to myself, oh, I have one thing, another thing. Oh, how am I gonna get a number out of them? I'm gonna multiply them and integrate. If I have two factors, derivative on the other on one side, well, by parts ultimately should allow me to transfer the derivative on the other side. That's what the fundamental theorem says. Okay. Any questions or comments about this? Now, the actual proof, as you see at this point, is not very illuminating. We somehow we define things in such a way that this proof actually makes sense. So it's almost like we started with the proof, and then we defined everything so that each step is legitimate. As far as I understand, that's actually what happened. But of course, the insight is the definition, right? So you redefine mathematical objects in such a way that the genius of yesterday becomes like the obvious syntactic thing. That's how math sort of gets, how math advances. Now, we still need a bunch of other things to define and stuff to state the general Stokes theorem, but ultimately, formally, it's going to look the same. Okay? Instead of a 0 form or a 1 form, it's going to be an arbitrary p form. Instead of a 1 cell, it's going to be a p plus 1 cell, whatever. But formally, it's going to look exactly like this. It's going to look like that over there. I'm not going to probably prove it. I'm just going to state it next week. Because ultimately, even though the proof is slightly more convoluted, because multiple integrals are going to be involved, it's of the same flavor, ultimately. We just follow the definitions. We defined everything. You trust the process. You trust the definitions. You just open everything up, reorder things, rearrange things, find a bunch of chain rule, whatever, and then you reassemble everything into a boundary. Okay. So this is another word for this is, of course, the fundamental theorem of line integrals. To match it with Calc 3, and you should be comfortable with this, how to use this, computing this, that, the other thing. Okay. Any comments or questions about this? I really want you to understand this. Once you understand one forms, one cells, all that stuff, generalizing becomes easier. Otherwise, it's going to get very abstract. OK, that's it for today. We don't have class on Friday because of Thanksgiving or Turkey Day. So happy Thanksgiving, Turkey Day. And I hope you eat lots of nice food. And I'll see you on Monday.